Hello all, this is Harshith Mukunda again. So I'm going to demonstrate the part 1 of the homework 6. So we are actually doing the high-level synthesis with Cyber Workbench using the no machine in the Linux terminal. So as you can see here that I'm trying to get the Cyber Workbench running, but since we have a very limited number of licenses, I'm not able to get the access to that. So I've just since I can't open the tool right now, I will explain the steps I followed to get all the results for my report using the lab manual as a guide. So I've already uh, written all the results that I've got when I had the access for the workbench. So these are just the results that I was able to get it and paste it when the access was allowed. So I've just completed the part 1. So just for the video, I'm not able to get the access to the application. So I'm just going to explain with the manual. So this is the manual that we were provided. So for part 1A, so I started by creating a new project. I just open the report and then just give a talk. So for part 1A, I just started by creating a new project as shown on page 2 of the manual. So I set the project options for the 50 megahertz clock by setting the clock period to 2000 and targeted the Cyclone 5 FPGA. So so this is where I changed things. So I've written 2000 here and then I've selected the devices and devices and the tags. So if you just look at this is the 50 megahertz. And then coming to the page 3, I inputted my AVE8.c code and then use the parse command or the analyze command to create the light view synthesis folder, which is this. And then coming to page 4 and 5, so in this I've ran the synthesize or generate RTL. This gave me my first set of results for 50 megahertz design. So so these are the data from the synthesize report. So I've got registers overall count to be 64, multiplexes to be 112, and then coming to ALUT 69, and then latencies to be 1, and then the overall functional units to be 7, as where we used 7 adders. So I've just written all the answers for these, and then for part B, I generated the logic synthesis script and ran the logic synthesis, the CUI command to compile the design in Quartus. Inside Quartus part 6, this worked. So in this report, it shows the comparison between the 69 ALUTs and 25 ALUTs, where the CWB used 69 and Quartus just used 25, and CWB estimated a delay of 2.054 nanoseconds, but the real world delay from Quartus was 9.544 nanoseconds. This shows that CWB report is just an estimate, and the real results after creation route are very different. So I've also attached the screenshots for these, and I've also written the discussion part. So coming to the part C, I rerun the synthesis at different frequencies where we have to change it for 4 times. So I just use the project option window where I had to change. So again, when I click on the project window, I get a display or tab like this. Yeah, this one. So again, I changed the values here. So for 200 megahertz, I make the period to be 500. So and then for 400 megahertz, I'll make it 250, and then for 600, nearly 167. So we'll be getting somewhere 598 or 99. So, and then if you just look at the results, so the latencies started changing for each of the devices. So for 50 it was one, for 200 it was good at one, for 400 it went on to 2 cycles, and then for 600 again it went on to 2 cycles, and then there's a slight differences in the delay. So if you look at this, the 400 megahertz at the max, where it was 3.2326 nanoseconds, and for 600 the delay had improved to 1.86. Although it still missed the target, no, this shows that the clear trade-off between clock speed and the latency. So, and I've also attached the screenshots to support the data that I filled in for part one. And I've also written the discussion, and then I've also chat GPT the same discussion to just give us the details on these. So, and these were the steps that I followed. So again, sorry I could not get the license working for the cyber workbench. So I just had to explain what all I did. So thank you.